Good evening, everyone. I'm Janelle Gurley, Director of Science and Programs here at Mineralogical Association, and it is my esteemed pleasure to welcome Dr. Darby Dyar this evening for our Science Speaker Series, our first Science Speaker Series for the calendar year of 2024. We're excited to return to everyone. And this evening, Dr. Dyar will be presenting Looking for Life in Our Solar System, a Mars-Earth-Venus comparison. A brief bio on Dr. Dyar before I turn the floor over to her. Dr. Dyar is the Kennedy-Schelkunoff Professor of Astronomy at Mount Holyoke College and Senior Scientist at the Planetary Science Institute. Dr. Dyar is a mineralogist and a spectroscopist interested in a wide range of problems relating to the evolution of the solar system. She studies the redox state of iron and the abundance of hydrogen in solar system materials using Mössbauer, X-ray absorption, and FTIR spectroscopy. Dyar has pioneered the use of machine learning tools to interpret spectroscopic data. She is the Deputy Principal Investigator on the VERITAS mission to Venus and was a participating scientist on the Mars Science Laboratory Science Team. Her honors and awards include the G.K. Gilbert Award for Outstanding Contributions to the Planetary Science from the Geological Society of America, GSA, the Hawley Medal from the Mineralogical Association of Canada, and the Eugene Shoemaker Distinguished Scientist Medal from NASA. She is a fellow of GSA, the Mineralogical Society of America, and the Geochemical Society. She earned her BA from Wellesley College and her Ph.D. in geochemistry from the Massachusetts Institute of Technology. Join me this evening in welcoming Dr. Darby Dyar. Welcome, Darby. How are you?
I am great. Thank you so much for inviting me.
It's our pleasure to host you this evening.
Okay, so shall I go ahead and share?
You are all set. The floor is yours. We're so excited.
Let's see. Okay, how's the sound? Can volume working out all right?
Sounds great.
Okay, yes. So let me get my screens oriented here. All right, so as Janelle gave me that wonderful introduction, it's really fun for me to talk about comparisons between planets that I work on. And I've spent my career working on not just lunar samples, but also Mars, Earth, and Venus. And so I decided to craft this talk tonight in a way that's really oriented around a question and that shows how we approach the answers to that question by looking at different bodies in the solar system, because I am, a comparative planetary scientist. Is what I would refer to myself as in this context. So let's get on to that most important question. So today I was looking on the internet to see what the most important human question is, and I found out that it is, who am I? Which it's a question I can't quite relate to, but the question I want to talk about is maybe the second most important question in human existence, which is the question of, are we human beings alone? Are there sentient beings anywhere else in the solar system? And this is a question on which we've made some progress over the course of my career. I've been in this field for 40 years. And when I started out, we didn't even think about exoplanets. Was there a question? No? Okay. But now we think about exoplanets a lot. And we think about them because we now know, well, we know, of course, that the universe is not infinitely large, but extremely large. And it is likely that there are places like Earth elsewhere in the solar system. And I think, elsewhere in the universe. I think we're only now starting to understand some of the parameters around that conclusion by looking at exoplanet research. And you may have sort of tuned into some of what's happening in the world of exoplanets. Every time I show this slide, I have to change the number on here. But there have now been more than 5,000 exoplanets discovered around other suns. And many of them are at Earth and Venus-like distances from their suns. And so even with this just very small sampling, it's sort of hard to imagine, to me, that there is another Earth-like planet somewhere around one of these exoplanets where there could be beings that are human-like. So this is the question that I want to grapple with tonight, and that is, what have the conditions been like on the three most likely planets in our solar system to have had life on them, Earth, Venus, and Mars? And hopefully from that, we can have some thinking together about what the possibilities are for finding life in other places. And why do I think this is true? Well, look at some pictures like this. So this is Venus and Earth compared to two of the Kepler discoveries. And, if you look at these planets, you think, oh gosh, they're the same size, they're the same distance from their stars. It's hard to believe that they aren't going to all be somewhat similar. And, the more you look at these things and you think about it, you have to ask the question, boy, as this knowledge about exoplanets explodes, what are we doing to answer it? And the answer is we need to look and think about planets close to us. And so tonight I want to talk about Earth, Venus, and Mars from this lens of exoplanet discoveries. And I'm not an exoplanet scientist, but as a Venus scientist, it seems like I become more and more interested in exoplanets because there's so many exoplanets that are being discovered that are, as I said, at Venus-like distances. So this is just a breakdown here. On the lower left, I'm showing you sort of the burgeoning science of exoplanets, all these discoveries that have happened. And on the right, the 5,000 plus, this is a recent slide, which shows that a lot of these planets, in particular, 4% of 5,000 are very terrestrial-like. And you also have to always look at these numbers with a grain of salt because there's an observational bias in how we discover exoplanets. Basically, the planet has to transit in front of its star, or between us and its star, in order for us to detect it with most of the methods that we use now. And so it stands to reason that the planets that are closer into the star will transit more often, and therefore it's more likely for us to catch a glimpse of them as they go around their stars. So think about that when you think about the biases associated with exoplanets. But this isn't really a talk about exoplanets per se. It's really a talk about one very simple thing, and that is water. So why do we care about water, and what's the link between habitability and water? Well, if you know anything about biology, you've probably seen this, this diagram before. In biology, we look at all of the species that have evolved on Earth, and we trace them back to the last universal common ancestor, Luca. And this, at least on Earth, this common ancestor was believed to have been originated in the Earth in what we call extreme hyperthermophiles. And I actually have been lucky enough to work on some of these hyperthermophile samples. Here's what they look like. You've probably seen some videos of these tube worms and these bizarre biological features that occur at mid-ocean ridges in these pipes. And I actually have one of these pipes sitting on my desk at Mount Holyoke. They're really fascinating. And what makes them fascinating is that they're chock full of microbes that can live in boiling conditions. So in the lab, when we grow them, we have to heat the water till it boils, and those are the conditions under which these things thrive. So these are the most primitive ancestors of life as we know it on Earth. And so in our human-centric life as we know it kind of viewpoint, we tell ourselves that if we're going to find life elsewhere in the solar system or in the universe, we need to be looking for places where there's liquid water. Now, you can question that assumption. Certainly, there may be life as we don't know it elsewhere in the universe, and there probably is, but we currently don't really have the, it's hard to develop a test to look for something that you don't know what it looks like. So admittedly, this is a what's the word I want? A limitation of this presentation, but I'm going to talk about life as we know it, and I'm going to begin by assuming that life as we know it originated in water, and therefore, if we want to find life elsewhere in our solar system or other solar systems, we would want to make sure that it's a place where liquid water is stable. Now, how common is that? Well, here's an example of a slide, sort of like what I often show in my classes. When a solar system forms, of course, it forms from a rotating disk of dust around a star. And as it gets hotter, as the star gets hotter and hotter, the rotating disk actually ends up with a thermal gradient. So unsurprisingly, it's warmest toward the star. So planets that form in the very innermost solar system will only be composed of materials that are solid at very high temperatures. And then as you go further and further away from the star, you cross into an area where you end up with things like ices being stable. And in the middle of our solar system, between Jupiter and Mars, there's what we sometimes call the frost line or the ice line, and that's the place where planets cease being stable for liquid water and start being icy giants. So now let's generalize this a little more, going back to an exoplanet. If you have a planet that is Earth-like and at an Earth-like distance from a star, then it's probably going to be in a temperature range that is going to be conducive to having liquid water present. And we refer to that in planetary science as the habitable zone. So the habitable zone at the moment in our solar system looks like this. And it's important when I show this to comment that I'm talking about right now. But if you were listening to what I just said, you'll notice that I said that a star heats up gradually. So in fact, the habitable zone actually moves around, right? Because as this thing gets warm, the planets closest to the sun warm up first, and then this sort of zone of habitability proceeds further and further out in the solar system as the sun heats up. Now, it doesn't move very fast, but when you talk about geological timeframes, it can move quite fast indeed. So, getting back to our theme of water, how do we trace the origin and the evolution of water from Mercury to Venus to Earth to Mars? Well, let's talk about this for a bit. So when that big dust disk starts out in the solar system, it's also in some ways layered by density. And as it happens, hydrogen and helium are very abundant in the dust cloud everywhere. So most of these planets have hydrogen and helium in them, but only a few of them have other elements. For example, there's more iron metals and sulfur in the inner planets, and of course more hydrogen and helium as you get further out. So in order to have a habitable place, you have to have a place that can have liquid water, which pretty much means that you can't be in an ice giant or a gas giant, because they don't have surfaces where water can be present. Okay, so now let's compare Mercury, Venus, Earth, and Mars. Actually, I'm not going to show Mercury because there's no evidence to suggest that Mercury ever had much hydrogen, and that's because it's too close to the sun. So there's also, in addition to a temperature gradient in a solar system, there's also kind of a gradient of hydrogen, if you want to think of it that way. So Mercury didn't have hydrogen, but Venus, Earth, and Mars all have had it. So let's take a look at this diagram and let me sort of parse you through it. So what I'm showing here is Earth, Venus, Mars, Mercury, and the Moon. And this is geologic time. So about 4.6 billion years ago is when the planets formed. And then on the right-hand side there is of course today. And then I've got some color coding on here, right? Orange is volcanic activity and tectonic activity, and blue is the thing we're interested in here, which is the liquid water being present on the surface. Now, many of you will know that water made its appearance on Earth about 4 billion years ago, and it's been stable on the surface of Earth ever since. And that's because we've pretty much been in that habitable zone for that whole time. Venus, on the other hand, if you look at this carefully, you'll see that Venus actually had liquid water before Earth did. And that's because as the sun was heating up and the sort of temperature gradient under which liquid water was present moved out from the sun, Venus became a place where there was stable liquid water far earlier than Earth. And in fact, there are recent climate models that suggest that Venus probably had liquid water on the surface for as many as 3 billion years, and I'll come back to that in a while. Meanwhile, little Mars, again, Mars is further out in the solar system, so it didn't get warm until a little bit later. And for various reasons, which I'll go into later, Mars only had liquid water for a short period of time. And of course, neither the Moon nor Mercury has liquid water to speak of. The Moon has some ice deposits in permanently shadowed craters. Mercury, there's no evidence for much ice there, except also from comets depositing stuff in permanently shadowed craters. So this is the story of water in our solar system. And as you look at this graphic, I want you to think about if you had $10 billion, say, or let's call it $100 billion, if you were NASA, where would you put your money to explore the origins of life? So the answer is going to surprise you because NASA didn't do the obvious thing, but they have devised this philosophy, which is if we want to look for life or habitable places, we need to follow water. And so the first of these planets to be studied in terms of extraterrestrial habitability was surprisingly Mars, and it was because of political reasons. I hate to say it. So some of you will remember who were born then. Back in 1996, a group of scientists at Johnson Space Center were studying a meteorite that was believed to have come from Mars. It was called Allen Hills 84001. It was found in Antarctica the previous winter. And researchers at JSC were looking at this under a very fancy microscope, and they found these things which they thought were organisms. And I remember this very well because at the time I was also studying meteorites from Mars. And the problem with these supposed microbes that they found was that they're too small. There's nothing on Earth that there's no segmented microbes on Earth that are known on Earth that have this geometry and that are this small. And at the time, it was really fascinating because when you work as a planetary scientist for a long time, the interrelationship between your ability to do science and the political funding that you need to do your science, it just continues to fascinate me. So what happened at the time was there was a lot of fanfare. There was a big news conference. President Clinton gave a special press conference on the possibility of extraterrestrial life. There's a lot of fanfare. And what's interesting looking back on that is that most of the scientific community, myself included, just kept our mouths shut. Why? Because we wanted the public to get excited about studying Mars, and we didn't really care what the motivation was or how flawed it was. We just wanted people to get excited about Mars. So, in fact, it did that, and it spawned a whole giant Mars program, from which many of us have benefited, and indeed, I would say the entire community of planetary science has benefited. So it just goes to show you here that sometimes even flawed science can actually make a difference in promoting good science. So a little interesting historical note there. So this set off NASA in a direction with enthusiastic support from Congress to do a strategy for Mars exploration. So they didn't actually pursue Mars because it was the most likely place to find water. It was because of this meteorite. So interesting the way this all worked out. But anyway, they developed this strategy for Mars exploration. They wanted to look for life, and therefore they were going to look for water. And so they wanted to find out when, where, the form, and the amount. And if you haven't been under a rock for the last couple decades, you're familiar with the fact that we sent a fleet of rovers to Mars. Starting with the Sojourner rover, which is one of my favorites, and of course culminating in the Perseverance rover that's up there now. But let's talk a little bit about the idea that maybe Mars wasn't the best place to look for water. And let's start with this little diagram. So sometimes people have the idea that as you go further out in the solar system, the planets get bigger. And that's sort of kind of true, but not for Mars. Mars is only 4/7 the size of Earth. And that has big implications for a planet because terrestrial bodies like Earth, Mars, Mercury, and Venus, they differentiate, which is to say that when they first form, they melt completely, and then as they cool, they become zoned with respect to the composition of what's inside of them. So interestingly, Earth, Mars, Mercury, and well, let's just keep it to Earth, Mars, and Venus. We're all kind of the same, made of the same material. It's mostly silica, aluminum, oxygen, materials that make up silicate minerals, except for the iron cores. But the size matters because if a planet starts out liquid, as it cools off, it's going to cool off faster if it's a smaller object. And that has profound consequences for what happens on the surface and how long water can last. So Mars, as it happens, cooled off faster, not only because it's smaller, but well, it cooled off faster because it's smaller. But that had a really unpleasant consequence for poor Mars, which is that it lost its magnetic field. Now, if you know anything about magnetic fields, I'll spring ahead to this little diagram. So magnetic fields, you may be familiar with them because magnetic fields are what brings us auroras on Earth. So the Earth has a dipole magnetic field. It's very strong. And so when the solar wind comes at the Earth, which is these little scratchy marks here on the side, the magnetic field does a very good job of rerouting those particles into the north and south poles. So that prevents us from being in a magnetic storm constantly. However, and where does that come from? Well, a magnetic field comes from a rotating conducting liquid in the interior. So it's that liquid part that's the thing here. Mars, because it cooled off fast, it lost most of its rotating molten liquid interior, and so it lost its magnetic field. And when it's lost its magnetic field, it has a little bit of what we call remnant magnetism, because there are some magnetic material minerals on the surface of Mars. But most of the surface of Mars is constantly being bathed by solar radiation. And that is sadly what caused it, what caused the conditions on the surface to, shall we say, deteriorate. Because you can't have clouds if you have the solar radiation continually bathing the surface. So I'm going to go back to this little comment. And in fact, if Mars had an atmosphere at the time that it might have had liquid water, it would have been broken down by this solar wind, because solar wind is really effective at breaking bonds between hydrogen and oxygen. And of course, that's what water's made of. All right, so now we know Mars had liquid water for only a very short period of time, but because not much has happened on the surface of Mars, we've seen evidence for the liquid water everywhere. And, this is the part of this talk where I wax poetic about rocks. So this is Curiosity. And I always have to brag on this. We built part of Curiosity at Mount Holyoke. It's this little thing back here in the back. So I'm very proud of that. This is a self-portrait, but in this case, in addition to bragging about my little piece of equipment, I want to show you that these are mud cracks. So this is an area where there was liquid water on Mars, and pretty much every rover that we've sent up there has found different kinds of evidence for liquid water there. So this is, I can't stop showing these pictures. So this is a really interesting place on Mars. It was one of the first places we stopped as the science team on the Curiosity rover. And these just probably look like, pieces of the sidewalk that broke off, or, concrete that fell off an old bridge. But in fact, to a geologist, these are pretty cool pictures because we have a scale on here. And because we know the scale, and because we can make measurements of the size distributions of these rocks, and not only the sizes, but also whether they're angular or rounded, that tells us a lot about how much time they spent in liquid water. And so, believe it or not, at this particular location, we were able to calculate that the water was moving at a rate of 3 feet per second, which is really cool. And in this particular case, it came from probably several kilometers away. So this was in a place called Peace Vallis, and it was a channel that fed into the alluvial fan, which is where Curiosity landed. So to a geologist, there's a lot of information in these things, and a lot of information about water. So this is sort of the smoking gun for the kind of water movement we probably saw on Mars billions of years ago. Here's some more evidence for that. These are sediments that were transported in stream flows. So see these cross beds here. To a geologist, there's a difference between cross beds that were formed by wind and cross beds that are formed by water. They have different geometries. And so by studying the shapes of these cross beds, again, we were able to determine just lots of cool things, like the direction the water was flowing, approximately how fast it was going, and maybe even things like how long it persisted in flowing in one direction or the other. So that's kind of cool. Now, moving forward, then let's get to the Perseverance rover, which is, of course, on Mars now. And this is what that locale. It's a little kind of a hokey thing, but it has Perseverance landed like right down in here. And the reason they landed there was because they knew that there was a channel that came across the plains of Mars and bridged the edge of this crater and flowed down into the bottom. And what I'm going to show you next are some of the pictures that resulted from that water. Oops, let's see if I can get out of this. There we go. So here's a boulder field. And again, you can tell by looking at the sizes of these things exactly how fast the water was flowing. And notice that some of these boulders are actually quite rounded, which means that they experienced a fairly long in people years, not so much in geologic time. They experienced a long exposure to large amounts of water. but it takes a pretty big water current to move boulders of this size. So lots of smoking gun for the days when there was water present on Mars. This is another classic example. This is a drainage channel. Beautiful thing. What's cool about the drainage channels on Mars is, when you think about like the Mississippi River, you all know that the Mississippi River is fed by tributaries that are all across the northern half of the Midwest, right? And then the tributaries join together and become the Mississippi River. Well, this water is not flowing from left to right in this picture. It's flowing from right to left. So the source of this is actually up here. And that's because the water channels that we see on the surface of Mars now actually come because something happens underneath the surface, some kind of volcanic event. And it basically gets close enough to the surface that it spontaneously melts the subsurface ice, and all of that water flows across the surface in a massive flooding event. So very different processes geologically on Mars from what we see today on Earth. There are also, well, we now know there are reservoirs of ice on Mars. The northern polar cap, which is more modern, actually is composed mostly of water ice, not so much the southern cap, but there's a lot of water in the atmosphere of Venus. I mean, if Mars is very transient, very thin, but it does have a lot of water in it. There are also glaciers now composed of water ice on the surface of Mars that have been extensively studied. And I like to show this because I'm going to brag on my student, Jay Dixon, who did this work. So this is a picture, it looks like a glacier. This could be Antarctica, but it isn't. It's Mars. And you can map these glaciers. They have all the same characteristics as Earth, as the ones on Earth. The same trim lines and tributary walls, and they have moraines where they stop, et cetera, et cetera. So striking, amazing glaciers on Mars. Now, and one other last thing I have to say, and that is, here's another really cool thing, from a paper that was published in 2005 that I always like to look at. So this is the same place, obviously. They flew over it multiple times. And the second time they flew over it, they saw this new deposit. So an eagle-eyed graduate student observed this new deposit. And what's interesting is they brought in a spectrometer to look to see if this was a different composition, and it wasn't. So it's the same composition. It's just I don't know. So it's made of the same phases, but maybe in different proportions. Well, we need more missions to Mars to figure this out. And then finally, I have to talk about Mars sample return. So part of this sort of propaganda train that led us into follow the water on Mars, starting back in 1996 with the Mars meteor, with supposed life on Mars meteorites. It got us to where we are today, which is that the penultimate goal of the Mars program has been to return samples to Earth. And so there is currently in the news a whole initiative called Mars Sample Return, MSR. And this rover, Perseverance, has been going around Mars, picking up samples and putting them in little tubes that look like this. And so they've essentially been like leaving Easter eggs all over the surface of Mars for some later mission to come pick up. And one of the ways that they might pick them up is using a helicopter like this. But right now, I have to say that Mars Sample Return is mired in politics and over budgeting. The Jet Propulsion Lab in the US has never built a mission. No one's ever built a rover of this size. The European Space Agency initially volunteered to create the spacecraft for Mars Sample Return, and now ESA is not as enthusiastic, I would say, about doing that. And it turns out to be technologically very complicated to retrieve samples. So, and there's a bunch of ways you can retrieve samples. You can just leave them on the ground like these Easter eggs that I just showed you. Or you can leave them on the rover, and the rover can drive over to what's called a fetch rover, and then they can be lifted off the surface of Mars and taken to an orbiter and brought back to Earth. But it's a complicated process. Now, that's all I want to say about Mars. But having said all of this, I want you to think about the fact that yeah, there are plenty of signs for there having been liquid water on Mars. But the question is really, was it long enough for life to have arisen there? And so I'll bring back this little diagram that I showed you earlier to show you that we now think that liquid water was present on Mars for about 300 million years. And if you know anything about the science of evolution on Earth, you would know that that isn't really long enough to have really gotten anything started. But on the other hand, we really don't understand much about the actual timetables of how life evolves. And of course, just because it took a certain amount of time on Earth does not mean that it would take the same amount of time on another planet. So anyway, I personally think that we would be very, very fortunate if we found any sign of life on in these return samples when we do get them back to Earth. And I gotta say, I don't know, of course I work on I work on engineering equipment to go on rovers, and it costs a lot of money to send a rover, but it costs like orders of magnitude more to send a rover to bring back samples, just as it costs an order of magnitude more to send a rover or to send a mission to Mars with humans in it, because it has to return. So I often ask myself if it's really worth it to return samples, but anyway, I digress. Let's talk about Venus, where there maybe is some hope for having found life. So again, to remind you, here's Venus. Here's a billion years ago, and Venus a billion years ago was in the habitable zone. And so maybe Venus had life because it had 3 billion years of liquid water in which in which life could reasonably have arisen. And there's been various claims about this. There was a study a couple of years ago that claimed to have found phosphine, which is an element that is associated with life on Venus. Turns out that this is another one of those, now politics intrudes into my talk again, because this is another example of it was an interesting discovery. The people probably released the information prematurely, but they thought it was such a hot find that they wanted to release it. And I think most scientists now feel like the data do not support the interpretation of phosphine on Venus, but it did help us get Venus mission selected. So I'm not going to knock it. I'm as you heard at the beginning, I'm the deputy PI on a mission to Venus, and I'm certain that this discovery got the public, and more importantly, in some ways, Congress, interested in Venus, and therefore probably was a contributor to the fact that we got selected. So let's think about Venus. Well, this is what Venus looks like now. This is a radar image, but this is what Venus could have looked like a billion years ago. It could have had liquid water just like Earth, which is an astounding concept. You know, it could have, although I got to remind you, life didn't really arise on Earth until less than a billion years ago. So there weren't whales swimming around on Venus. At least I don't think there were whales swimming on Venus, but still, there was certainly plenty of time for microbial life to have arisen on Venus. And where would it have arisen? Well, Venus it's a fascinating planet. I've been interested in Venus for 40 years. It's just that we haven't had very many missions there, so it hasn't really been an opportunity. So one of the things that's really interesting about Venus is that the entire planet was resurfaced somewhere about a couple 100 million years ago. So all of this, this is a radar image, so it looks funny. All this dark stuff is basalt. So something like 89% of the surface of Venus is covered by what we think are basalt flows. We don't actually know because we don't really have good analytical data from the surface of Venus. But then there's this 11% of Venus, which is these sort of white crinkly terrains. They look for all the world like if you take a piece of aluminum foil and crumple it up and then try to smooth it back out again, you'll get all these little lines. So these are topographically high areas that are called tessera. And tessera, some people believe, are granitic and possibly remnants of plate tectonic activity on Venus, and also possibly places where there were continents and where there could be life. So certainly places like these tessera will be areas where we will go look when we start looking for evidence of life on Venus. But unfortunately, Venus is a really difficult place to study because it's so hot. And being a hot planet has a lot of implications that you may not think about. So, for example, this slide shows you these white things. In a radar image, the smooth stuff is bright. So these smooth objects here are rivers of lava. And on Venus, the rivers flow like 3 times farther than lavas do on Earth. This particular image is an image of a river that is literally the length of the Nile River on Earth, but it's not water, it's basalt. So we know from evidence like this, and also from some missions that have made it to the surface, that the surface temperature on Venus now is a very warm, 460 degrees C, so quite warm. So clearly there isn't liquid water on Venus now, but at some point in the past there was liquid water, and then that raises the question of, was there life there? I can never resist showing other cool things. These are sand dunes. I don't know if you can tell on your screen, but these little places here, you can see they have kind of an orientation to it. So these are sand dunes. Now on Earth, sand dunes form in the presence of water. So gee, isn't it curious that there are actually sand dunes on Venus, although there's also sand dunes on Mars. And then there's also a lot of wind. There's quite a bit of on Venus, sorry. There's quite a bit of atmospheric circulation on Venus, as witnessed by, this is a little impact crater, and you can see it's got quite the tail where the wind picked up the sediment that came out of the impact and blew it away. Can't resist some of my other favorite features on Venus. These are what we call pancake domes for obvious reason. And people, when this image was first produced, people christened it the pancakes floating in a sea of syrup. But these are intriguing lavas that for some reason they come out and they're highly viscous. So instead of flowing out like all the other lavas that I just showed you, they form these high steep walled features, which are called pancake domes. And we think that they're very high in silica, which is the reason why they're so sticky. And that's important because on Earth, we don't get silica-rich lavas except by virtue of plate tectonics. So this is a feature that we find associated with plate tectonics. And so many people think that the pancake domes are evidence of there having been plate tectonics on Venus. And now you're thinking, well, what do plate tectonics have to do with water, Darby? Well, plate tectonics, almost by definition, is a way of recycling volatiles that are at the surface into the interior and then bringing them back up to the surface. So plate tectonics has a lot to do with recycling volatiles, and that in turn has a lot to do with the creation of oceans and then habitats, if you will, for a life to arise. A couple other just fun pictures. These are what they call tick volcanoes on Venus. It's very cool. Strange profiles. And then this is a chain of coronas. Coronas are these giant volcanic features on Venus that never quite make it to the surface, but they just push the surface up. They're kind of like what's going on in Yellowstone. Fascinating. And they're believed to be maybe associated with something having to do with plate tectonics. So here's some pictures. These are the only pictures we have, not just some pictures. These are the only pictures we have of the surface of Venus. These are all from at the time Soviet landers, Venera 9, 10, 13, and 14. And you can see they look like basalt flows. And some of these missions also had geochemical equipment on them. And the compositions look basalt-like, but unfortunately the error bars on these analyses are extremely large, and so we're not kind of not too convinced. But anyway, they didn't have any analysis of water on the surface, so we don't know if these lavas on the surface have water in them, which we would dearly love to know. But when you look at these, you can't help but think, okay, this is like Venus right now is just this horrible wasteland. And these pictures have been color corrected because you have to realize that at 480 or what, I'm thinking in centigrade, not Kelvin, the rocks glow. So they look like, they look like this color. So understanding what's going on the surface of Venus is complicated by the fact that the rocks glow, and it's not your normal planetary surface where you can put a rover down and wander around. But I want to talk a little bit about what's happened at Venus, because I think we learn things about habitability from studying Venus that we can't learn in any other way. And that, of course, has to do with the greenhouse effect. Now, as I said earlier, the solar system, the sun heated up, and the location where Venus was in the solar system started to get hot. And when it did that, something unfortunate happened to Venus. Now, remember that on Earth, we have roughly the same amount of CO2 and water as Venus does. But on Earth, we store our CO2 in the deep oceans in the form of fossils. If we didn't have deep oceans on Earth, the CO2 that is stored there would end up back in the atmosphere, and we would have horrible global warming. So that's, of course, exactly what happened to Venus. Venus got hot. As Venus heated up, the water evaporated. Once the water got into the atmosphere, some of it started to get picked off by the solar wind, and the rest of it, what was left of the CO2, all ended up in the atmosphere. CO2 is harder for the solar wind to break up. And so the net result is that, unlike on Earth, where we have this lovely cycle of being able to store our CO2 in the oceans, the minute you lose your oceans on Venus, you lose your, what's the word I want, your sink for CO2, and CO2 ends up in the atmosphere, and the surface of Venus ends up looking like, well, you can't see it because it's got this horrible thick ray of clouds, and that's made it actually very difficult to design missions around. And one of the things that we're doing on the VERITAS mission that I'm working on is we had to develop a whole new kind of spectroscopy using machine learning that can penetrate these clouds. So to sort of, summarize all this, the greenhouse effect is the thing whereby visible light can get through the cloud layers, both on Venus and on Earth. But when the energy gets re-radiated from the surface, it's no longer the same wavelength, and it can't get through the clouds. And you've probably all seen explanations like this of the greenhouse effect. The energy comes in as visible sunlight, some of it gets reflected, but the rest is absorbed, and some of it gets re-emitted, but it's now as infrared light and it can't get out. So different ways of doing that. So now the ta-da moment of this talk is we're going to go to Venus, and I can't help but brag a little bit about my mission, which is called VERITAS. We're going to study all these factors that are expected to impact the habitability of Venus. The past oceans on the planetary surface. We're going to look at the tessera and see if those are continental roots. We're going to look at the atmosphere on Venus and see if there's water outgassing, because one of the ways we tell if a planet has, one of the ways we study the water budget on a planet is to look at H2O, water being outgassed from volcanoes, because that tells us something about the cycling of water on a planet. VERITAS is also going to look at tectonic activity, and as I said earlier, plate tectonics, because of its role in recycling volatiles, has a lot to do with habitability. And then we're also going to do things like look at the internal energy budget and examine the magnetic field, because, as you know from my discussion of Mars, magnetic fields also have a big role to play in figuring out how something may or may not lose its atmosphere. So the VERITAS mission will launch either in 2029 or 2031, and we're going to answer all these questions that you see here, which I'm really excited about. And of course, the reason we're going to tie that all back to my beginning is because we think there was water on Venus. Now, I'm just going to conclude this talk with just a handful of slides here about Earth. Many of you in this audience are all probably very familiar with what the data look like. Every time I download the newest data on these, like this morning, I was Googling atmospheric CO2 2024. This is the latest map of atmospheric CO2 at the Mauna Loa Observatory, and I find it profoundly sad. And I look at other graphs like this, and I think about the relationship between surface temperature and CO2, and I wonder about the future of our planet. You do worry about that as a planetary scientist in a very educated way. I don't think that we are going to go the way of the way of Venus anytime soon. I would not lose sleep over it. It'll probably be a couple billion years before the sun gets too hot and the Earth starts to get fried the way Venus did. But I think it's interesting to see that the same mechanisms that happen on Venus also operate on Earth. And in fact, that is one of my favorite things about being a planetary scientist, is the universality of all of these concepts, that what happens on one planet often happen on another planet. That's sure, the boundary conditions may change a little bit, but the net result is always quite similar processes, and we can learn from comparing them. So this is my last slide, which goes back to my question that I started at the beginning. Are we alone? I don't know. This talk can't answer that question. And in some ways, it remains without enough data. And so it really is a philosophical question about what is the role of, what is the distribution of life as we know it in our solar system or in exoplanets and the universe in general. If you want to know what I think, I think that if we could look hard enough, I think that we're going to find evidence for some kind of bacterial, microbial life on Venus. Maybe even not in my lifetime, but we're going to find it, I bet, on Venus. Mars, probably not so much. And in fact, in my bad days, I worry that the US government is spending countless billions of dollars to bring back samples from Mars that are going to look exactly like the meteorites that we have from Mars. And that would be very discouraging. But I think we have to keep looking for this, because I really do believe that if we can understand the uniqueness of life and whether we on Earth are truly unique, then that really is one of the most profound questions for human existence. So on that statement, I will tie things up and I'll be happy to take questions.
Dr. Dyer, thank you so much. That was very compelling and fascinating. I definitely am hooked on all your findings. I know that we had one question come in already, so I'll kick off the Q&A session with our first question. And my box just disappeared. From Alan, can life develop in liquid methane?
Probably. The answer is probably. There are people working on that. So I would say stay tuned, because of course we're now really interested in looking at some of the satellites of the outer planets, and that's going to be a really important question. So I think the answer is probably yes.
Awesome. From Celia, hi Darby. Thank you so much for such a wonderful.
Hi Celia.
I felt like I was back in your special seminars at Mount Holyoke. All my best, Celia.
Aw. Hi Seal, I miss you.
I feel like I can speak for her in saying that I know she misses you as well.
Aw.
And we at the MMA miss you too, Celia, just so you know. All right. And while we wait for people to, what's the word I'm looking for, marinate on some questions, I have a few questions for you. Did you always want to be an astronomer? Can you tell us a little bit about your trajectory from your academic experience all the way to where you are in your career now?
Oh, well, no, oh boy. This is the part where I say, oh, all you young high school students out there, you really want to become a scientist because it's the greatest thing ever. And all of that is true. But when I was in high school, I hated science. I grew up in Indiana in the 1960s, and in order to graduate from high school, I only had to take 1 year of science. So I took biology, which I hated. And the environment conspired to convince me that I couldn't do it. So it wasn't until I got to Wellesley and I had to take a science course to graduate that I finally realized, oh, well, maybe I can do this, because I'm a very visual learner and geology is a very visual topic. So I decided to go to grad school. You know, so I ended up studying, and I actually double majored in art history and geology.
Oh, wow.
And ended up going to grad school, and the funding I had in my first year was to work on lunar samples, because this was in the 1970s. So we'd just gotten a bunch of lunar samples back. So that kind of got me interested in planetary geology. And I ended up doing sort of normal field geology for a bunch of years. And then I came back to planetary science when I came to Mount Holyoke 25 years ago, where I ended up in an astronomy department, even though I have to confess I've never taken an astronomy course. Taught plenty of them. But so, you know, my career is sort of, life is what happens to you while you're busy making other plans. Right. But you know, society has changed a lot since I was in high school, and I'm really glad it has. And that's one of the reasons why I'm happy to make presentations like this, because one of the reasons I never thought about being a scientist is I never saw a woman who was a scientist until I got to college. It just wasn't part of my frame of reference. So anyway, so that's my story.
Well, it's a great one, and definitely one that is filled with inspiration. And I think that we can all heed and learn from that. That even when you can't see yourself in a certain frame, it doesn't mean that you should always fully exclude yourself from that frame of reference.
Yeah, so. Exactly.
Question from Joel. You mentioned reasons for why oceans disappeared on Venus. Why on Mars? I might have missed that.
So, okay, sorry, I clearly didn't explain it very well. So Mars lost its magnetic field because it cooled off and its interior stopped circulating. So the minute it stopped circulating, it stopped having that magnetic shield. And when Mars lost its magnetic shield, the solar wind stripped the hydrogen out of the atmosphere. And essentially, once there's no atmosphere to protect the surface, any liquid water just was carried away by the solar wind. So that's how it lost its water. Sorry, I didn't make that clear.
It's okay. Sometimes it's great to hear it twice, or even 3 or 4 or 5 times. Why the name VERITAS for the mission?
It stands for, I don't even know the acronym. That's terrible because I'm the deputy PI. So this is a funny story. So, when you propose a mission to NASA headquarters, you have to come up with an acronym.
Okay.
So we wasted, and I do mean, well, I guess wasted is the wrong word, but we spent many, many, many hours trying to figure out an acronym that would be half palatable. And that's something I find myself doing on every single mission I'm involved with. And it's almost comical sometimes. Because, and there's also a lot of politics involved in it. You can't, it can't be
right.
It can't be derogatory to any particular group or country or planet. So it's quite a process. But it stands for Venus Emissivity and surface radar. So it's basically, we have 2 instruments. We have a spectrometer, which measures the emissivity or the energy being given off by the surface. And then we have a radar instrument, which will do topography, which make a topographic map of the surface.
Awesome, thank you. From an anonymous attendee, do you think there's water or ice on asteroids? Any efforts underway to research this?
Yes, I think there is. We have done a couple things where we have, there was a mission called Deep Impact, where they basically threw a piece of spacecraft junk at the surface and then took the spectra of the gas that was kicked up and it had hydrogen in it. So yes, we think there's water in asteroids. In fact, a lot of people now think that some asteroids are actually leftover cores of comets. And of course, comets are surrounded by water, ice water, or water in the form of ice. So yes, a lot of asteroids have water either on them or in them. Any asteroid that's big enough to have had impacts, if a comet impacted an asteroid, it will always deposit ice in the crater. And if the crater is shadowed from the surface from the sun, then the ice will persist. So there's different ways you can get ice into an asteroid, but yes, asteroids also have water. So the problem is, of course, asteroids are small and oftentimes, well, they're not, most of them are not big enough to have differentiated. So the water isn't liquid, it pretty much stays as ice, which is not to say that you can't also, life can thrive in ice. Now, whether life could originate in ice, man, I don't know the research on that, so I can't comment on that.
Fair. When rather, did you get involved with the science laboratory team, the Mars Science Laboratory team?
So interestingly, part of my research, as you could gather from my comments, has to do with had it been possible for me to be an engineer, that's what I would have been. Had the playing field been level for me as a high school student, I love taking things apart and putting them together and designing things. So shortly after the Mars Science Lab got selected by NASA, which was maybe like 2000, I heard that they had this really cool new instrument that was I'm an analytical geochemist, so I work with all, as she said, all that sort of ABCs of different kinds of analytical techniques. And I was reading the press release about the equipment that was going to go on MSL, and they said they had this new thing called a LIBS, which is called laser induced breakdown spectroscopy. And what LIBS is you fire a weapons grade laser at a rock and you melt it into a plasma that's at 10,000 degrees C, and then you take a spectrum of the plasma, and from that you can tell the chemical composition of the object. Well, I just thought that was the coolest thing ever. So fools rush in where angels fear to tread, right? I emailed the PI and said, hey, my name is Darby Dyar. I'm an analytical geochemist. I've worked on calibrating instruments like that. Would you be interested in having me work with the mission? And so he emailed me back and said, sure. So long story short, we ended up, as you saw, building part of the mission at Mount Holyoke, and I got to be on the science team, which was a really fun experience. And we actually have a clone of that laser in my lab at Mount Holyoke. So we, often if we were, if this was a different talk, I could show you little movies of plasmas that we take spectra of. It is pretty cool.
It sounds like we have to host you again and have you back so that we can do that. Jeremy asks, is it more difficult to send probes to Venus than it is to Mars?
Getting there, no. It turns out that Mercury is the hardest one to get to because of the gravitational pull of the sun. But no, it's pretty straightforward to get to Venus. And I have to say, I've been fortunate to work with, so at the Jet Propulsion Lab, there are, they have, I don't know, they have 1,200 employees. There are 2 guys that do the orbital trajectories. So they design the trajectories for all these missions that you read about, just these 2 guys. And the code for doing it is incredible. It takes like 48 hours to do 1 run.
Oh, wow.
And a lot of things that I didn't know before I started designing missions are things like the moment when you leave Earth actually ends up propagating into exactly not just when you're going to get to the planet, in our case Venus, but also where you will be on the planet when you arrive. And so for example, our mission is going to cover the entire surface 11 times, but we kind of wanted to start in one particular place. In fact, we're trying to start in the area where the landers were, because we're trying to use, we have ground, what we call ground truth, right? We have ground truth where the Soviet landers were. So we're trying to come in over the place where the landers were. And every time headquarters pushes our launch date back, we have to go through this whole thing about recalculating our trajectory. So anyway, the answer to your question is it's Mars and Venus are pretty easy to get to, to the extent, but these models that they have been proven, over and over again, and they use the same models for everything. So, but it's a very fascinating. The people that do this are just geniuses. But it's really interesting.
And to piggyback on that question, in terms of the data capture, how instantaneous is that, or what's the time lapse?
So you probably know that, when you're, well, of course, it completely depends on where the 2 objects are in the solar system at the time, right? In fact, when I was working on Mars Science Lab, I didn't realize that we would get a vacation for, I don't know, a couple days, maybe it was more like a week and a half, when Mars was on the other side of Earth and it couldn't relay stuff to us.
Right.
So that for Venus, it's going to be similar to Mars. So anywhere between, I don't know, half an hour to circa half an hour. It's not instantaneous.
Right.
And that's another interesting thing too. When you actually are running a mission, you have to think about these things. So NASA operates something called the Deep Space Network. And this is an important governmental asset, interestingly. I just was a couple months ago at a talk, and it turns out that this is part of the Pentagon. They think about the Deep Space Network as a defense asset also. But the Deep Space Network is not infallible, and there's only a handful of transmitters everywhere on Earth. And so it is the case, no matter what object you work on, the moon, Mars, Venus, an asteroid, whatever, that oftentimes you don't get your data back in a timely fashion because, the weather is bad in Australia. or you get the data back, but there's a huge hole in it. It can be kind of frustrating. So a lot of what happens when you're doing a mission, and when you're actually doing what we call mission operations, mission ops, is you're trying to figure out, well, for example, on Mars, we were often trying to figure out how much data can we get back from the DSN in time to make the decisions we need to pilot the rover tomorrow. And which data do we need? And, can we, like, for example, the images don't come down as high resolution images. They come down as thumbnails. So that part of it is also really interesting, and it's all, if NASA has multiple missions, then we are wheeling and dealing with the other missions that are up there at the same time, trying to make sure that we don't step on their toes. So lots of behind the scenes politics around how you get the data back.
It sure seems it. Can you tell me a little bit more about your study of diverse rocks? I might have done a little bit more peeking in your other bio statements. And I read about the rocks from Antarctica, the lunar rocks, which you talked about a little bit, and deep ocean rocks.
So let's see. So I started, well, I started my career as a geologist actually working on, believe it or not, metamorphic rocks from the state of Maine, where I now live. And then I moved to looking at mantle xenoliths, which are rocks that originate somewhere between 60 and 80 kilometers deep in the earth and get brought up on by special kinds of magmas that bring things to the surface at the speed of a freight train. So I studied those, and then I got interested in meteorites because meteorites are a whole different breed. You know, there's many different kinds. They have various mineralogies, and you can learn fascinating things from them. And my research is very tedious. What I do is I take meteorites and I actually smash them up and hand pick out the different minerals so that I can analyze the different minerals. So it's incredibly tedious, but it's really interesting. I'm trying to understand how oxygen, because oxygen it's the most commonly occurring element in the crusts of terrestrial objects, but yet it's highly variable and it's also very difficult to measure. So my real long-term research interest has been trying to understand how oxygen is distributed among these planets. And of course, you know, going back to the talk, oxygen influences habitability, right? So it turns out to be a really important question. And then the lunar samples, that's just fun. My PhD thesis, I was looking at, so the moon has the volcanoes on the moon, some of them are particularly volatile rich and they erupt as fire fountains. And because there's no atmosphere on the moon, or very little atmosphere on the moon, when fire fountains happen, the magmas quench as glass droplets and they rain back down on the surface. So almost like 20% of the regolith, the soil on the moon, is composed of these little glass droplets. And so for my PhD thesis, I was trying to understand whether the droplets were formed by fire fountains or whether they were formed by impacts, because impact has the same net effect, you know, energy or kinetic energy and thermal energy makes a big melt. And it turns out you can't really tell the difference between a glass droplet that was made by
Kinetic versus
by a volcano versus an impact. But I'm still studying them. They recently, you may be aware that when they brought the Apollo samples back, they put some of them away, excuse me, for 50 years, and then they recently unsealed them. So I was fortunate enough in both the past two competitions to be given some of those samples. And darn it, I'm still working on lunar glass beads, but it's, you know, it's still fascinating. And now I'm using synchrotrons to study them instead of gamma rays. So, you know, life has a way of giving you second chances to look at problems that are still really, really interesting.
Coming full circle, for sure. So can we expect to see more work in this area from you in the future?
Oh yeah, I still have, I have a safe full of lunar samples at Mount Holyoke, and I'm still working on them. Although I'm retiring from, excuse me, from teaching, it's going to be a long time before I will retire from doing planetary science because it's just too fun.
The research will continue. We love that. Where do you envision the field of astronomy or geochemistry as it relates to your study in astronomy? Where do you envision us being in the next 100 years? And I know that can be a loaded question.
Ooh, that's a great question though. Oh man. Well, geochemistry, our ability to analyze things is to me amazing. You know, the fact that we have microscopes where there's a microscope that I use at Johns Hopkins University that you can look at the arrangement of individual atoms in a material. So, you know, what we choose to do with that technology is going to be really interesting. But I think, you know, the real answer to that question is machine learning. You know, you can call it artificial intelligence, which I always think is a funny name for it because it's really about using the information that we've collected and building models to predict situations that we can't anticipate. So I think that all fields of science are going to be affected profoundly by the ability of machines to learn. But at the same time, machine learning is indeed just that. It's learning based on existing data. And so I think that in the next 100 years, we're going to see this interesting interplay between, you know, the analytical techniques, the computer techniques are going to be way more sophisticated than the data that we have to train them on. And so I think it'll be an interesting push-pull where people go, oh, well, now we've got to go back to basics and collect some more data so we can
Right.
build better models. So I think that's going to be ubiquitous across all the scientific fields.
I like that position. That even though the technology will be more advanced, it's only going to be, its capabilities are only as advanced as the amount of information that it can access. So
Yep, exactly.
ultimately, it still needs the human.
Still needs humans.
perspective.
And I think there will always be, I mean, I consider myself a person that does fundamental science. I don't really, I mean, the engineering stuff is applied science, but I think there's always going to be a role for fundamental science, fundamental data
Right.
to build models on. I don't see that going away anytime soon, although it's not very glamorous. You know, sometimes it's hard to
Right.
get, believe it or not, fundamental research. NASA doesn't want to fund fundamental research right now.
Right.
That, you know, when this changeover happens, they're going to realize, oh yeah, we have to go back
Invest
and
in it again.
Yeah.
Definitely. I agree with you on that. Question from Peter. Any idea how many of your Mount Holyoke students have pursued science careers based on having taken your courses?
Oh boy. You know, as I think about retirement, I think about that. I'll give two answers. The first one is that every year I go to the Lunar and Planetary Science Conference. I've been going to that meeting for 50 years. And about, I don't know, 20 years ago, some of my former students said, hey, Darby, you want to meet me at a bar? You know, so we got this tradition on Tuesday night, we would meet at a bar at 5 o'clock. Well, this is snowballed, and now there's like 50 people at this thing. So these are all people who have persisted in the field of just planetary and have gone on to great careers. I would say that, well, at Mount Holyoke, more than 50% of our students go on to do graduate degrees. So if that's your measure of success, then I feel like I've been very successful. But in fact, my measure of success for teaching in some ways is less about the astronomy students and more about everybody else. I actually teach the introductory course, which is for non-scientists at Mount Holyoke. And, you know, in some ways as an educator, that's almost more important. You know, the science students like you, Seal, I'm talking you're going to major in science and you're going to do great regardless of whether I'm out there. But I don't know, as an educator, I'm actually more vested in making sure that the non-science students graduate from college knowing what an error bar is,
Right.
you know, knowing how to interpret a line on a graph, you know, sort of those fundamental concepts of quantitative literacy. So yeah, I think I've probably taught 10,000 students in my career, maybe. And you just never know, you know. I've had people come back to me or write notes that say, you don't remember me, but I went on to do such and such, or I enjoy talking to my kids about rocks, even though I'm a journalist, you know. So you never know, you know. I feel like teaching is like casting a pebble into a lake. You just don't know where the ripples are going to go.
Right. And how far out they go sometimes. Yep. What? My brain just timed out a little bit because I melded two questions in my head. Yeah. Wow. Okay. What do you, no, I asked you that already. I'm sorry. What is one question you hoped that I had asked, or that you hope someone else had asked that we haven't covered yet, that you feel like it's important information for you to convey with our listeners and our viewers this evening, or the masses?
You know, I'm not going to be political, but I am going to say that, you know, the scientific way of thinking depends on looking at data and making interpretations of the data. And, you know, apropos of controversies like climate change, when I teach climate change in my classes now, I don't actually give students an interpretation. I just show them slide after slide of the data, like the ones I showed you tonight. And I guess my, you know, the most important question would be, what is the most important thing that you teach? And I think the most important thing that I teach is have the confidence to make interpretations based on facts. And if everyone in the world made interpretations based on facts, I think the world would be a better place.
And oftentimes we conflate facts with feelings, it feels
Yes.
like lately. And as a scientist myself, that is something that weighs heavily on my mind that, we're not really making those data-driven decisions, and it doesn't have to be as complex as we make it seem often. But stick to the facts and drive the decisions off of the facts.
Yep.
I like that.
Yep. I mean, with my own children, I'm famous for saying, well, now let's think about the data, kids, and the
Right.
children will groan. Oh, no, not that, Mom.
Like, what's the raw data we're working with?
Yes, exactly. That sentence works in many, many parts of my life.
It's definitely a transferable one, for sure.
Yeah, exactly.
What are your plans for the upcoming solar eclipse this year? Where will you be for it?
So I don't know, I'm torn. We're going to have a big party at the observatory at Mount Holyoke. We got a grant from the college and we bought 4,000 pairs of eclipse glasses. But so I don't know. I either will be at Mount Holyoke or I'm going to sneak up to, we have a family home in New Hampshire, which is on the line
On the path.
on the path of totality.
Yep.
So I haven't made a decision yet. I have to decide if I'm going to be selfish or unselfish.
Yep. That's fair. Take your time in deciding. There's no pressure, and you don't have to tell us which one you decide. What's next for you, apart from the VERITAS mission and you continuing your study of your lunar rocks and all your diverse rocks? What else can we expect from Darby on the horizon?
Oh boy. I want to do more, what's the word I want? I'm on the Space Studies Board of the National Academies, and in that position, I'm able to affect science policy, which I find really interesting. I'm also going to make more quilts and walk my dog on the beach a lot.
Yeah.
So after 37 years of teaching, I'm going to try to take it a little more slowly, and my children would be thrilled to hear me say that. But it'll be nice to be able to just do my research and not always be carrying the burden of trying to be the best possible teacher and role model all the time.
Yeah,
that's a heavy load,
It is, and I love the start of this new chapter for you. I really, really do.
do.
Be more present and more balanced. I like that. Well, Darby, it's been a true honor and a pleasure to share time and space with you this evening. And I know I speak for our viewers and our listeners this evening that it's been such a wild learning experience in the best way from you. I really hope to have you again. You are a treasure and a wealth of knowledge. And sincerely, from the bottom of my heart, thank you so much for making time for us this evening for our Science Speaker Series.
It's a pleasure. Thank you so much for all of you for listening.
Of course. We are better for it.
All right. Have a good evening, everyone.
You as well. On behalf of the Mineralogical Association, everyone, have a great evening. Thank you again, everyone.